This is Math 139, Section 1.7. We're going to look at solving quadratic equations using technology. First of all, I want to go back to something that you already know about solving a system of equations from our work on linear equations. If you have a system of equations like this one, y equals negative 2x plus 9, and y equals 3x minus 11, we could graph both of those lines. Right? This is the negative slope, so this one must be y equals negative 2x plus 9. And then this blue one is the y equals 3x minus 11. From the graph, we can actually read the solution to this system. We're looking for a point that lies on both lines, which would be the intersection point. In this case, it looks like that would be x equals 4 and y equals 1. So that is the solution to our system. We could have also solved this system by hand using a substitution method. If I just took this negative 2x plus 9 and substituted it for the y in the second equation, I would have negative 2x plus 9 equals 3x minus 11. That is a fairly simple equation to solve. We'll add the 2x. Let's see, add the 11. And then dividing by 5, we see that x is 4, which is exactly what we saw from the graph. And then we could just go back and take that x equal 4 and plug it in for the x in either of our original two equations to figure out the y. I'll just go ahead and use this bottom one. 3 times 4 minus 11 would be 12 minus 11, or 1. And there we go. X is 4, y is 1. Same solution we saw in the graph, of course. All right, where are we going with this? Well, think about the equation that we wrote after the substitution. This one right here. That could have just been an equation that we started with, right? We didn't necessarily have to get it from here. And we could have really solved that equation exactly the same way that we did this one. We could have graphed this side and gotten the red line, graphed that side and gotten the blue line, and looked for the intersection point. That leads us to the technique that we're going to use for solving quadratic equations graphically, or really, for that matter, any equations graphically. If we simply graph each side as a separate equation and look for intersection points, we'll have the solutions to our system, or to our original equation. One subtle point that's worth talking about. Yes, we could have used our graph to solve that equation. However, there's one difference between the solution to this equation and the solution to the system. This equation only contains the variable x, so the solution would just be x equals 4. The fact that the y value is 1 may be true, but y was not part of the original equation, so we wouldn't include it. We'll keep that in mind as we solve other systems graphically. So, what this suggests about solving any equation using graphing technology? If I have an equation, and I'm just going to say it looks like this, the right-hand side equals, well gosh, I got that backwards, didn't I? How about this? The left-hand side equals the right-hand side. Then what I can do is graph y equals whatever that left-hand side was, and also graph y equals whatever that right-hand side was. And where they intersect is really going to give me the solution to my equation. Keeping in mind the point we had here, the solution to the original equation would not involve y. We would only use the x value for that intersection point. We're only trying to solve for x. All right, let's take a look at how this would work in a couple of examples. In example 1, we've got two graphs in the picture. Y equals x squared, of course, is our parabola, and y equals 2x plus 3 is our line. Just by looking at this graph, we can see that this system of equations has two solutions. There's one intersection point over here and another one there. It looks like they are -1, 1, and 3, 9. Now look at what happens when we again think about that substitution method. If I take x squared and substitute it for y in the second equation, my new equation would look like this. Just by looking at the graph, I already know that the x values form the solution to this quadratic equation, and I already know that those x values were -1 and +3. Let's verify this by hand. We certainly know how to solve that equation using a by hand technique. If I have x squared equals 2x plus 3, I could subtract to get it equal to 0, right? When you have a quadratic equation, most of the time, getting it equal to 0 is the way we want to start. And I'm going to factor that trinomial. It is a 1x squared, so I know I can start with x times x. And then I'm looking for a sum of -3 and a product of -2. Let's see, that would have to be what? Boy, that doesn't work because I've got it backwards. Let's try that again. A sum of -2 and a product of -3. That's better. All right, now I think we can use -3 and 1. So x minus 3, x plus 1. If x minus 3 is 0, then x equals 3. And if x plus 1 is 0, then x equals -1. And those are exactly the solutions that we had up here. So everything seems to be working out just fine. All right, let's start another example. And this time I won't give you the system. We're just going to go ahead and start right out with the quadratic equation. In example 2, I'd like to solve the equation -x squared plus 9 equals x squared minus 5x plus 2. We'll begin by breaking this down into a system of two equations. First, I'll let y be the left-hand side, -x squared plus 9. And then I'll let y be the right-hand side, x squared minus 5x plus 2. We'll generate the graphs of those two equations using Desmos, and then the intersection point will help me to solve the original equation. So let me switch over to Desmos here. Get rid of our old stuff. And our first equation was -x squared plus 9. And our second one was y equals x squared. Oops, let me get the y equals in there. Minus 5x plus 2. And there we go. We've got our two equations, and I can see an intersection point right there, and another one over here. Now remember, the original equation only contained x's, not y's. So the solutions that I'm looking for are just the x values, -1 and 3.5. So x equals -1 and x equals 3.5. All right, how about this one? In example 3, we would like to solve the quadratic equation 3x squared plus 2x minus 4 equals 0. If I'd like to express that as a system, I could write y equals the left-hand side, 3x squared plus 2x minus 4, and then y equals the right-hand side, y equals 0. We'll generate those graphs, but before we do, let's think for a moment about y equals 0. That's really just the x-axis, isn't it? I'm going to graph it on Desmos, but then we're going to talk about whether we really needed to graph that or if we could have gotten the information we needed without it. So back over to Desmos. The first one was y equals 3x squared plus 2x minus 4. And actually, before I even graph the y equals 0, let's come on over here for a second. We know the x-axis is y equals 0, and we really can already see where that graph crosses the x-axis. The x-intercepts are something that Desmos finds for us automatically without us having to graph the actual y equals 0. Just to kind of be really clear about it, I will go ahead and also type in y equals 0. Let me change the color on that. See it a little better. There we go. But notice that the intersection points are exactly the same as those x-intercepts, which is always going to happen whenever 0 is one side of your equation. It seems pretty clear to me that this was probably an irrational solution. What I'm seeing here are approximations. And of course, that's the best I can do with technology. I'm not going to be able to see solutions that have radicals in them if I'm using a graph to solve my equations. Our approximation, then, is x is approximately -1.535, and x is approximately 0.869. And there we go, our two solutions to our quadratic equation. And again, this is just what we talked about. When one side was equal to 0, we really could just find the x-intercepts. What we often called the zeros of the function, rather than actually graphing the second equation, the y equals 0. All right, we also talked a little bit about this. These probably are not exact values. So what we could do is find exact values by hand and then just sort of compare them to what we saw using the technology. My equation is already equal to 0. Let me just write that down right here. And if I'm thinking of factoring that, I would need a sum of 2 and a product of -12. I need the A times C method here for my sum product. And I don't think that's going to work. 1 times 12 won't do it. 2 times 6, 3 times 4. None of those are going to give me a sum of 2. So factoring is not a good option here, or not an option at all. Let's use the quadratic formula. So let's see, I would have a -2 plus or minus the square root of 2 squared minus 4 times 3 times -4 over 2 times 3. Let's see, under my radical here, 2 squared is 4, minus a negative is going to make that plus, And 12 times 4 is 48. So I actually have 52 under the radical. And 6 on the bottom. If all I wanted to do was check my decimal values, I could actually put this in the calculator right from here. But just for a little practice, we haven't done it for a few sections, let's go ahead and simplify this first. I'm going to break that 52 down as the square root of 4 times the square root of 13. So that would be 2 times the square root of 13. And I notice that every single term is divisible by 2. So I'm going to divide by the form of 1, 2 over 2. And I'll get negative 1 plus or minus the square root of 13 over 3. Let's just check that out and verify that I get the same decimal approximations that we got from our graph. If I take negative 1 plus the square root of 13 and divide by 3, I get 0.869 approximately. And if I take negative 1 minus the square root of 13 divided by 3, about negative 1.35 or 535. And those, you'll notice, are exactly the same values that we had from the graph. Let me just jot them down here. And again, if you go back up and compare, that's what I found on the graph as well. So decimal approximations, not exact values, are what we're always going to get from a technology or graphical solution method. All right, our last example for this section, I'd like to solve this quadratic equation. Let's once again break it up as a system of equations. The left-hand side, I would want to graph y equals 2x squared. And the right-hand side, y equals x minus 5. So I'm going to pop on over to Desmos. Two x squared was my left-hand side, and x minus 5 for the right-hand side. Now what you'll notice here is that these two graphs never intersect. There are no intersection points. Therefore, there are no solutions to this system. However, we were able to find all quadratic equations had solutions when we worked them by hand. So let's solve this by hand and see if we can figure out what's going on here. Using that same quadratic formula, let's see here. Oh, I probably should have, I'll do it off to the side. We do need to get this equal to 0. So I'd have 2x squared minus x plus 5 equal to 0. And so minus b would be a positive 1, plus or minus the square root of negative 1 squared minus 4 times 2 times 5 over 2 times 2. Under my radical, that's 1 subtract 40, or negative 39. And I suspect you can already see what was happening here with the no solutions. There actually are solutions, but with the negative under the radical, the solutions are complex numbers. We're going to get an I in here. And we can't see imaginary numbers on a graph. So we're going to say not just no solutions, but no real valued solutions. In fact, the actual solutions could be written as 1 plus or minus I times the square root of 39 over 4 for complex solutions. So the lesson learned here is that if we are going to use graphing technology to solve our equations, graphing technology will only find real valued solutions. If we're interested in complex solutions, the graph's not going to give them for us. So graphs only find real valued solutions. Not imaginary solutions. All right, that brings us to the end of section 1.7.